Welcome everyone to the final lecture of section 1. So this is the end of the plate tectonics material. Section 1 started with an introduction to the course, then an introduction to the Earth's creation and a little bit of the formation of Long Island. We identified our water bodies both globally and locally. Then we dove into plate tectonics with 3 lectures technically. We had the beginning portion again, which introduced us to the dates and times and the theory behind the formation of these locations, and then part A and part B of plate tectonics, which covered plate tectonics itself, divergence, convergence, and transform movement of plates, and then got really deep into the theories, the scientists, the dates, and the proofs behind both continental drift and plate tectonics. This final lecture, I'm going to share it with you now, is going to be about ocean basins. Lab number 3 and portions of lab number 4 are going to help you to better understand this material as well. So we're going to come full circle and catch up essentially with lab material to match the lecture material. Again, once we finish this lecture, we will have completed section 1 of the course. And the next thing we'll do is a review and then have a test. But let's first finish up the material. You've gotten through the hard part, the plate tectonics part, understanding convergence, divergence, and transform, being able to identify where those things are occurring on maps, knowing what's happening with the geologic events and the causes. It's a little bit hard to grasp. This lecture is now a physical and visible description and view of essentially what's happening as the plate tectonic activities have occurred. So what's the remnants, what's left over? It begs us a couple of questions. Okay, question 1, if we know that seafloor spreading is happening in the middle of mid-ocean ridge systems where plates meet, and we know therefore that the middle of the mid-ocean ridge system is youngest and tallest, and the edges are oldest and deepest, what exactly does the bottom of the ocean floor look like? More importantly, in putting it with an oceanographic spin, what is the topography or bathymetry of the ocean floor? And that literally just means, what does it visibly look like if you were to draw a relief map, right, with highs and lows of what the ocean floor would be? Now, first things first, what you can notice, we've seen this figure multiple times now, okay? The Earth has 8 major plates and 8 minor plates, roughly. And when you look at a photo like this, you can see that there are shallow areas represented in blues. Okay, those are along the coasts surrounding a lot of what we call the continents, but they're also along the mid-ocean ridge systems. There's one in the Pacific. Okay. So we know, of course, that those lines that I've just drawn are going to be your shallower zones. For example, in the Atlantic mid-ocean ridge, it's youngest in the middle and shallowest in the middle. Then these dark blue areas are representing where it's deeper. We also know that that also means not only is it deeper, but it's older. Okay, so if we were to drain this picture of all the blue and literally just have our plates, we'd have our continental crust and our oceanic crust exposed. Again, oceanic crust would be here, here, and newly formed ocean crust would be here. Continental crust starts there. Okay. So if we drain that, what's it going to look like? Well, we didn't know right at first. So we started off with doing echo soundings, which is essentially bouncing sound off of particular beams that go through the depth of the water. And they hit and stop essentially, and then you can read a relief or a reverse map. It confirmed, of course, what we knew from plate tectonics, that the ocean was not deepest in the center, because again, that's where the mid-ocean ridge is. So it's actually shallow there, and that the deepest part of the ocean did in fact lie at the edges. So here's a visual explaining how sonar works, how echo soundings work, and giving you what those relief maps look like. So now you can see that there are higher points, which again would be shallower in an ocean, and lower points, which would be deeper in an ocean. Now this is pretty and easy for you to see. What actually comes out on the boat are soundings like this. But what it does, no matter what, is it tells you deep and shallow locations. Why do we need to do this? Well, it's important to map the seafloor, one, so that we can find cool biological areas like hydrothermal vents, which you'll hear about at the end of this lecture. It's also important because it does impact currents, and it impacts how the ocean systems are moving. And if it's really shallow, of course, it would really matter if you were a boat, and you need to know what's underneath you. From a biological perspective, also, it can influence where fishing grounds are and how migration paths of a lot of transmigratory fish like sharks may travel. So what they've done is given you an example of a transect from the North American plate, there's the edge, okay, to the African plate, and there's the edge, okay? And they transect, of course, through deeper and older sections and shallower and younger sections. And that translates exactly to this figure up above. So here's our mid-ocean ridge. Sure enough, it is shallower there. The edges match up with the deeper ocean basin. And then we hit back up on land again. You're going to then be mapping this type of figure in Lab 4. And you're going to do one map for the Atlantic Ocean and a series of maps for the Pacific Ocean. And you'll be labeling them as such. You'll label the mid-ocean ridge, you'll label the margins or the sides, and you'll label the ocean basin. What this lecture is going to do now is focus specifically on what does it really look like. Okay, so right now we have a bunch of dots and high and low points, but what physically is there? So we're going to look at what happens in the ocean basin floor, and we're going to look at what's different and happens in a continental margin. You'll notice that continental margins, like the margins on a paper, are on either side. Okay, so just one more example before we start getting into some of the definitions and nitty-gritty of this stuff. I want you to realize that you're going to be doing an Atlantic Ocean transect. Okay, here it is, and a Pacific Ocean transect. Notice there's a massive difference. You see no mid-ocean ridge here in the Pacific example. Instead, you see some things that are indicative of, think about it from plate tectonics, what are trenches indicative of? Subduction or convergence. So here you have seafloor spreading and a divergent plate boundary. So that's representative, of course, off the coast of North America and off the coast of South America. And if you leave off the west coast of North America or off the west coast of South America, you have an entirely different type of plate tectonics. You then have subduction instead. So of course the relief maps or the bathymetric maps should look different, and of course they do. This is one of my favorite pictures. I actually have a picture of this hung up in my office because I think it's so beautiful. But it shows what I call the backbone or the zipper, which is our mid-ocean ridge. And here's the center of the mid-ocean ridge. Remember, it's never a straight line. Why? Because it's separated regularly by faults, right? Where things are going to slide laterally, just like a sliding glass door. But it does in fact show you that there's a mountain in the middle of the ocean. That mountain is called the mid-ocean ridge. On either side of it, it gets deeper and older until, of course, you hit continental crust as you get to what we call the parts of the plates that you can see flying overhead in an airplane. Okay. So let's make sure we understand where we are in this lecture in relation to the lecture that we just covered with plate tectonics. Okay. So here's our mid-ocean ridge system. This is representing divergence. Okay. We know that that's seafloor spreading. What's happening there? The basalt that is in the asthenosphere, so here's where the convection current of the asthenosphere would be, can push through this area, causing the divergence or the separating of oceanic crust. That oceanic crust will form new in the middle, so that's basalt, pushing this apart. Remember, those are stages 1 through 3 of the Wilson cycle. That means that this entire plate, okay, is shifting to the left. It is being pushed up and out of the way. Why? Because if this is basalt and oceanic crust, and this is granite, which means continental crust, they're two densities. Granite is less dense, so it gets pushed up and out of the way. It then becomes the edge of the continent, or specifically, we're going to call the edge a margin. So the continental margin is made up of a series of locations. Again, the water is filling over that section, but it's in the deeper portions that it meets up and then becomes shallower as, again, here would be the beach where you would lay your towel. So what we've just done is we've left our mid-ocean ridge system right here in the middle. We've gone across the ocean floor, and then literally right here where you see a change in topography, change in coloration, you know you have a margin. And the margin is a shelf, a break, a slope, and a rise. The rise is the location where it meets the deep ocean floor and allows for sediment to build. We know these things are true because, again, the echo soundings have shown us that, and it happens over millions of years. Again, think back to the lecture before this. How many millions of years can this boat travel until it gets to the edge of an ocean? Hopefully you said the date was Pangea, right? So about 200 million years ago. So this boat in this example has a lot more space to travel. So if the topography of the ocean floor is going to cover two components, the continental margins and the ocean basin, what we're really doing is showing that this is the continental crust, again, granite, which is less dense, and this is the oceanic crust, which is basalt, and that's more dense. So here we go. This is your classic figure for this particular lecture. This is the figure that you should spend the most time with. Go back to it, study it, memorize it, work with it, use it when you're doing your quizzes, use it when you're doing your work, use it when you're doing your labs. It's the perfect figure to explain exactly what's happening when the ocean floor meets, or the ocean floor, remember, is oceanic crust, when the ocean floor meets the continent, when it meets the continental crust. So take a look where this continental margin is extending from. From the area where you would lay your towel, okay, literally where water meets land, to the edge of where the ocean floor meets. In other words, everything here is granite, and everything here is basalt. So stuff that you would find in the deep ocean floor is going to be different topographically than the stuff you're going to find in the continental margin. So the margin has four components. Okay, they go in order from closest to shore to furthest from shore. I'm just going to change the color. Open it back up again. Change the color of my drawing. Okay, they go from shallowest to deepest or closest to shore to furthest offshore. They are the shelf, the break, the slope, and the rise. Again, shelf, break, slope, and rise. They go in that order. By definition, the continental shelf is a submerged, shallow extension of the continent. Again, what you can see here is that it is at or just slightly below sea level, okay, 0 essentially kilometers, and then gets slightly shallower. That's a shelf. You could lay a plate on here, right, or ride your bike and you'd still have to pedal a little bit. Then you hit a spot where if you were riding a bike or rolling a ball, you literally would stop pedaling and you would just have a free fall. It's a hill. That hill, of course, is called a slope. Okay? At the exact meeting point of where the shelf meets the slope, we call that the break. That's the place where you go from the submerged, shallow extension of the continent to the actual hill. The final component here is the erosion or the sediment mound. This is on top of the actual and connected to the actual slope and continues up until we change from granite to basalt. You'll be labeling all of these things in your Atlantic Ocean figure for Lab 4. So again, you're going to have them on both sides of that map. Here's another figure that I think equally shows you a great perspective of how these four components are. Remember, the entire thing is called the continental margin. A margin means edge. So this is the edge of where the continental crust meets the oceanic crust. The oceanic crust is more dense, so it's pushed down. Continental crust, less dense, so it's pushed up. Okay, so this is what's under the water in the deeper portion. This is what's under the water in the shallower portion, and then literally above sea level at the edge. The entire margin has 4 parts: shelf, break, slope, and rise. Once you get past the rise, you're in exclusively oceanic crust. See how where the margin ended? So this is your ocean basin. Okay. Here's a physical, pretty beautiful image, I believe, of the Florida coast. So here's your shelf. That is your break. That's your slope. And that's your rise. So that's where the erosion is. Anything past here, of course, is going to be deep ocean basin. Remember though, if we've gone down on one side of a plate and then met at the middle of a mid-ocean ridge, this must of course happen on the other side. So what goes up must go down, because if you think back to plate tectonics, we need isostatic equilibrium. Everything has to balance. So where there's a deep, there's a tall. So of course, from a plate tectonics perspective, if you have a margin on one side and a mid-ocean ridge in the middle, you should have a margin on the other side. So notice you have 2 margins, just like on paper, 2 edges, right? 2 1-inch margins, or half-inch, whatever you set it as. So it's showing you that you have a middle, aptly named the mid-ocean ridge. In the middle, what is happening to form this rift valley? What is happening to form that mid-ocean ridge? Divergence. Okay, so we know that so far, seafloor spreading is occurring there. And then we know that it's young and shallow, and it has to get deeper in the ocean basin as you go to the left and to the right. But it only gets deeper until you hit your margin. So there's the margin on the left, and there's my margin on the right. Notice that the margins are not the same distance from the middle, and they don't have the same topographic features. On this side, you just have an abyssal plain, which is sort of a flat, featureless area, and again, your 4 components of the margin. On this side, you have things that are indicative of subduction. So over here is convergence. Okay. We still have our margin examples, but they're much steeper and they end at an actual trench. Another visual showing you the same thing. On this particular side, we have flat, featureless rises on both sides, opening up from the mid-ocean ridge system. So this is a divergence only example. Okay. What it's showing us, of course, is a margin on either side, giving us our shelf, our break, our slope, and our rise. Our shelf, our break, our slope, and our rise. Mid-ocean basin, exclusively in the middle. Now we've talked about the word margin, right? And we've called it a continental margin. There's actually 2 types of margins, passive margin and active margin. And these literally match up with which type of plate boundary it's located by. Passive margins match divergent plate boundaries, and active margins face convergent plate boundaries. So a convergent plate boundary is going to be where there's a lot of activity because you're close to a subduction zone. In a passive margin, there's not a lot of activity because you're near just seafloor spreading, newly created seafloor. I'm going to go back to the figure that we just saw and remind us one more time of these margin types. So here we are. Here's our mid-ocean ridge system. This means this is divergence, right? This divergence is causing this plate to shift and move to the left on this side, and it pushes up the continental crust on this side. Because it's facing a divergent plate boundary and it's far away from the mid-ocean system, it's a passive continental margin. Now over here, you still have divergence, right? Divergence is here. But before you get to the margin on this side, what did you get? Convergence. So of course, this side has to be an active margin. In the next example, we literally have only a mid-ocean ridge system, okay, only divergence. So this is passive and this is passive. What you do, of course, is you interpret the boundaries to figure out where you would have active and passive margins. So here's a figure of the United States in the center there with the rest of the Earth and all of the land masses. It's our 7 continents, and we're not looking at a plate map right now. We're looking at, as you fly overhead in an airplane, where the continents and all the land masses are that stick up above water. And anywhere that you see a green line is telling you that it is a passive margin. So let's make sure that this makes sense, okay? Here we are, okay, east coast of the United States. We know that our mid-ocean ridge system is right in the center of the Atlantic Ocean. So if this is a divergent boundary right here, then you better have a passive margin on either side, which makes sense. Okay. Over here, though, you have a convergent plate boundary along with a whole series of trenches that let us know that that convergent boundary is there, along also with a series of fault lines. And because of that, you don't see any green. So this over here is an active margin. Passive margins here, all along the Arctic as well, and surrounding Australia. Everywhere else is an active boundary. Active margins, of course, are going to match up with the opposite side, where convergent boundaries are and transformed plate boundaries are. So if you were to look at an example, this is the South American plate, but it could equally be the North American plate. It's the same answer, okay? If you were to turn it on its side and look at the west coast, versus the east coast. On the east coast, what do you see? A mid-ocean ridge system, telling us exclusively that this is divergence. If this is divergent, then this side of the plate must be a passive margin. Conversely, on this side, what do you see? A trench. That trench is telling us that it's a subduction zone or a convergent boundary. That means that this plate, the Nazca plate, is actually subducting underneath the South American plate. South American plate is pushing up. So over here, in opposition, you have an active boundary. I want to show you one more thing on this figure. Give me one sec. On this figure, the next thing that I want to show you is that you have a difference of the actual margin width, okay? Notice how it's called a narrow shelf. The shelf is part of the margin, and here it's called a broad shelf. Again, shelf is part of the margin. So if you have on the west side, if you have a convergent boundary, you have an active margin and a narrow shelf. On the opposite side, if you have a divergent boundary, you have a passive margin and a broad shelf. It's a really big distinction. Remember, the 4 parts of the continental margin are shelf, break, slope, and rise in that order. You're going to look at the shelf. If it's narrow, that's telling you that it's active and that it's part of a convergent boundary near a trench somewhere. If, in opposition, that shelf is broad, the opposite must happen. You have a passive margin and you're near a divergent boundary. So when you do all of your graphing and mapping and have to label these things, you're going to be able to look at the width of the shelf and if it's narrow or broad, you can tell the difference, in addition, of course, to knowing if it's near a trench for a mid-ocean system. So the remaining components, again, if you're looking at the larger PowerPoint, the remaining components here will then give you each text slide of the definitions of the shelf, the break, the slope, and the rise. Moving on, we've now covered the margin portion in its 4 components: the shelf, the break, the slope, and the rise. There's one more physical feature that can actually occur in the continental margin that hasn't been mentioned yet. It's called a submarine canyon. A submarine canyon, as it's defined here, is formed by turbidity, right? It's sort of like a bunch of sediment coming from higher up and carving out a cut in the shelf and on slope. We call it a sea fan at the bottom, okay, not a sea fan, the marine organism. A sea fan meaning it looks like a bunch of sediment has spread out on the sea floor. And this happens starting at the shelf and going down the slope. Okay, so this is all part of the margin still. Okay, so this is still going to be continental crust. This happens because there's a rush of water from a river or some sort of upland runoff carving that canyon out. Our most famous canyon, you can see it here. Okay, so here's Long Island. Our most famous canyon is in New Jersey. So this would have been a level, even continental margin, broad and flat. But there becomes this deep cut right here, right where that submarine canyon is. What this does is it allows deep ocean water and the organisms that are in it, like sharks and big fish, to swim up into that canyon. So a lot of people who like to fish love to fish near what we call the canyons because it allows for really good sport fishing. Of course, what it does is it just mixes different types of water because of the different depths in the ocean. The bathymetry changes, which is exactly what this lecture is talking about. If we move on out from here, okay, so now we've covered 5 components in the margin: shelf, break, slope, rise, and the one specific example of the submarine canyon. But what happens if we move outward, out into the deeper ocean? Well, we know, first of all, the first thing that happens is we change from granite, which is over here, to basalt. We know we go from older crust to younger crust. But what else happens? Well, what's going to happen is, first thing you're going to find is a thick layer of sediment where essentially the continental rise meets the basalt rock, which is forming and smashing up against the granite rock at the margin edge. Okay, this makes up a huge portion of the Earth's surface, more than half. And you're going to find along that seafloor a whole bunch of features. Okay, we call these ocean features. Now, some of which you already know, right? So first and foremost, the largest ocean feature that we've talked about is the mid-ocean ridge. Okay, so we know that that's, of course, in the middle of the seafloor. We've also spoken a lot about trenches. Trenches are formed in subduction zones at convergent boundaries. These others, though, other than maybe having heard about them before, we haven't really spent a lot of focus. So the rest of this lecture is going to go through all of these different features of the seafloor. This particular figure has a couple of examples, okay? 2 different examples: seamounts and what we call table mounts. These can also be called guyutes or guyuts. Depends again what textbook and what person is talking. They start at the divergent boundary where seafloor spreading is, and a seamount, okay, is submerged. So it has to be under the water and pointy, as opposed to a table mount, which is also submerged, but it's flat. So they're literally just submerged portions of the ocean basin crust, basalt crust, that are under the water and either pointy or flat. A seamount has a pointy tip, and a table mount has a flat tip. The only other evidence that you see here are things above sea level. We already know what those are, right? Anything above sea level we call an island, Over time, though, if that island gets pushed away, because remember, these plates are shifting to the left and to the right, so as that island moves further and further over the years, it will eventually sink. So we talk about, for example, the lost city of Atlantis, right? There could have been an island up above the sea level that was habitable, and over time, millions of years, it sunk, which then made it inhabitable for humans, at least. And they then become, after an island, a seamount, and then it erodes away, like getting a flat top haircut. It erodes away and becomes a table mount. Even further away than that, of course, you're going to have to go down in depth and down in elevation, right? Going down an island. What actually happens on these outer edges? Well, you're going to find that you're going to have that original island system. If you were to look under the water here, you would find seamounts and table mounts in these areas not exposed, again, because they'd be below sea level. And on the opposite side, what are you finding in this big, vast expanse? That's the rest of what the ocean basins are going to cover. So, in other words, an island arc is the highest, tallest component, followed next by a seamount, getting deeper in the ocean, right? Less tall, followed by a table mount, even deeper in the ocean and even less tall, followed, of course, by the abyssal hills and the abyssal plains. These are going to surround those trenches. Those trenches are going to be at the edge of where the plate boundary meets, okay? Now at that exact same location, of course, you're going to have to find what's left. So imagine that an island is here, again, above sea level. When that erodes away and moves further away, you get a seamount, submerged but taller. When that erodes away, you get a table mount or a guyute, even deeper down and flatter. Erode that away and you get abyssal hills and abyssal plains. Abyssal hills are just slightly higher than the plain, which is the deepest part of the ocean. We call that the flat, featureless portion of the ocean. Those are all components of, literally, the oceanic crust. Remember, other components of the oceanic crust can always be trenches and mid-ocean ridge systems on the opposite side where a dive boundary would be. If you follow the trench line, remember, these are active margins. So if you follow that trench line, it makes sense that those active margins follow that same location. We can then assume that in this portion of the ocean, you're going to find your islands, your mounts, your table mounts, your abyssal hills, and your abyssal plains. Another visual of the same thing. Finally, our last feature. Now, I'm a marine biologist. I also teach oceanography, of course, and knowing marine biology sort of goes hand in hand with oceanography. But from a marine biological perspective, the most fascinating part of this entire lecture is that in the part of the ocean that you would think is the deepest, darkest, scariest, hardest to live, we find a true thriving biological community. It's called a hydrothermal vent. Hydro, water, thermal, temperature, vent, opening. These occur at the exact same location that the mid-ocean ridge systems are. So again, here's our mid-Atlantic ridge. And sure enough, we have a series of thermal vents that have been discovered all along the center of that ridge line. They are a true community of a collection of material that can serve as food, so chemicals essentially that can serve as food at the spreading center. And along this chimney or this volcano or vent, we actually end up with food sources, chemical food sources for marine organisms. Those marine organisms can feed off that smoke, which again is filled with chemicals and elements, minerals. And that chemical material can be synthesized through something called chemosynthesis by marine organisms that can literally cement themselves on the vent. So this would be the opening of the mid-ocean ridge system. There's the smoke or the material coming from the asthenosphere. If this were above the water on an island, that would look red like lava, okay? It's because it's so cold here, but the material that's coming out of the vent is so hot that it precipitates into what looks like this black cloud. But this black cloud can actually rain down chemicals, which serve as food all of these marine organisms. Now here we're showing you tube worms, which is probably the most popular and famous of all of the marine vent communities. There's a close-up. These are called Pompeii worms or fireworms. But you can also see mussels, and these are eyeless and colorless shrimp. A whole series of organisms live along these vent communities. Pretty amazing. So what's pretty cool is that we have life independent of the sun. If anybody's interested in watching a video more about hydrothermal vents, just cut and paste this link right here into your browser, and you'll watch a really cool, unique video about the vent systems. So you want to remember, up on land, in the presence of oxygen, we use photosynthesis. We need sunlight. At the bottom of the ocean floor, sunlight cannot penetrate. So we still have carbon dioxide, but instead of having sunlight, we use chemicals. In this particular example, sulfur is the chemical. So instead of synthesizing light, you synthesize chemicals. Either way, you're making a food source. And those marine organisms are going through a process that is the exact opposite of photosynthesis. Right? So in photosynthesis, we take in dioxide, cleaning our planet, of course, and we produce oxygen. In chemosynthesis, you still have carbon dioxide, but we also use oxygen plus some sort of chemical material, and we produce hydrogen sulfide, sulfuric acid, and the food source for the organisms to live from. So you've taken essentially an inhabitable location, at the deepest, darkest, highest pressure, most likely to be named location that you would find nothing living in the planet, and you have a huge diversity of marine organisms. We believe that the importance of the vent bacteria, which live inside the gut cavities, a lot of these marine organisms that allow them to chemosynthesize chemicals, the importance of that vent bacteria may link back to the possible origins of life. Archaea, extremophiles, right? Organisms that are 4 billion years old. Pretty crazy. If you're into this sort of thing, you want to make sure that you take a marine biology class in the spring or whenever you're available. We spend a lot of time talking about specific marine bacteria and bacteria as a whole and their importance in the marine community, as well as looking at hydrothermal organisms and deep sea organisms. So just to summarize, I want to cover the second half of this lecture one more time, make sure that you understand what we've just covered. So the lecture began with introducing what a continental margin is. It's the edge, and going over the 5 components that we could find as topographic features on the actual margin. Continental shelf, continental break, continental slope, continental rise. Those are all made of granite and part of the continental crust. You may also find a submarine canyon if there's erosion or turbidity coming from upland in that location. When the continental rise meets the ocean floor, we change from granite to basalt. And in the ocean floor, we have a series of features. Our features include mid-ocean ridges, which again are not shown in this figure, trenches, which we know occur from convergent boundaries, island arcs, which we know occur again at the other side of the convergent boundary, the trenches pushing down and the landmass, which is an island, pushes up. Moving further out into the open ocean and going deeper in depth and now under the water, we would have a seamount, a table mount, an abyssal hill, and the flattest, deepest, oldest part of the ocean is the abyssal plain. We finally end with our unique biological community that is found at the mid-ocean ridge system. And we've now come full circle. That is the end of section 1 material and section 1 of the course.